This must be that bog. Yeah. There's a trail we should have come down. I was aiming for. Yeah. Hello everyone, it is May 30th, 2021, and today we are going to talk about this hill behind us. It's hard to see, but there is rock exposed under the brush there. I have a piece of it in my hand, and the property owner was nice enough to let us take a look. But I need to say something first. You might hear me refer to dates as like 1890. When I say that, what I mean is 1,890 million years ago, or 1.89 billion with a B years ago, just so you know. You're also going to see some slides with millions of years ago as well. But something very interesting is here. The rocks are highly deformed and metamorphosed. Any corrections, especially those involving dates, will appear on the screen as I am talking, so watch for those. But what you can see here is this one looks really weathered, this white. What's so interesting about this rock behind me? Well, you've heard me talk about ophiolites before, and that's what we have here. This is the base of an ophiolite sequence right here. This is as low as we can get in a typical ophiolite sequence in northeastern Wisconsin, of all places. Now, an ophiolite sequence is a bit of the ocean crust that, through tectonics and continental collisions, has been thrust upon the land. It's basically a chunk of ocean crust from about the surface of the ocean floor, in this case, down through the lithospheric mantle, but it doesn't have to be all the way down to the lithospheric mantle. Remember, the lithosphere is involved in plate tectonics, part of that plate recycling, and it consists of the crust and the very upper part of the mantle. It's important to remember that. Now, as the density of old crust increases, you get a new subduction zone, and this may cause a chunk of the oceanic crust to be thrust upon another chunk of crust, usually a continent or an island arc, something like that. And this process is called abduction. Now, in a lot of papers, especially 21st century papers, you'll see the term supra-subduction instead of abduction. To me, this term is confusing and redundant and not necessary, since we already have a word for it. But that's how things sometimes work out. I don't see the point of using a term that means like subduction, that means, one plate going under another, then slapping the word super in front of it. But, it appears in papers, so I'm letting you know about it. And that's what we have here. And this is actually, from looking at it, this could be the physical moho near the crust mantle boundary. That's what this rock looks like. It's highly ultramafic. So this may be an actual place about 900 feet above mean sea level where you can take a chunk of rock that is right at the crust mantle boundary. I don't think we have any mantle rock here. I will have to determine that by doing petrographic analysis, which I can't do in the field, but we are at least at moho level here, the physical moho. There's a seismic moho, but that's a talk for another time. So what was going on here? Well, we have a terrain called the Pembine terrain, and technically we are on the north edge of that around here. The Niagara Fault is up there, Tim's Lake is up there, more of the ophiolite sequence is exposed up there, but you're higher in section. Here you're as low as you can be in it. This is a geologic map of the area that I made based off the limited field data that I did collect. It is based off Sim's 1989 map, and as you can see, we only have two bedrock units here. We have an upper ophiolite and a lower ophiolite. The upper ophiolite is that big, massive sheet dike mafic basalt. The lower ophiolite is where I am standing, which I believe is a chunk of the ultramafic moho. I generated a generic cross-section based off the limited data that I did collect. According to my interpretation here, more work still needs to be done. I do believe that this moho bit is an anticline, a rather tight anticline, which does make sense considering the fact that we have upper ophiolite surrounding us on all sides. We don't know exactly how old this is. We do know that the 12-foot falls diorite intruded this rock. We do have a date for that, so this has to be older than that. How much older? We don't really know. It could be 1900 million years old, but it's likely a little bit older than that further down into the Ophiolite section that you go. So we weren't able to directly date this, and people have tried. That's a common problem with ultramafic rocks. They don't usually yield good datable material, as I know from personal experience trying to do the Presque Isle Peridotite up in Marquette. Tectonically, what happened is this Pembine terrain, which seemed to be an island arc, all right? It started to move north, which would be this way. So we had subduction, a plate going under it to the south as it was coming this way, slowly accreting to the superior craton. And as it did that, whenever the subduction going that way started, it dislodged a piece of the ocean crust with the bit of the mantle and pushed it up in the front of it, giving us this Ophiolite sequence, which does continue all the way to the Niagara Fault Zone. And if you go to Tim's Lake and stuff like that and walk along the trails, you will see dark mafic rock, although you're higher up in the Ophiolite sequence there. But it's all over the place there, and it trends about east-west. The dip does vary a lot because it has been compressed, but that east-west trend is consistent. So anyway, once this Pembine terrain accreted to the superior craton, something happened. The marsh field terrain began to approach as well. But the marsh field, something happened. We no longer had a south subducting plate. The plate started subducting to the north. Why this happened, I don't know. Cannon and Schultz are the leaders in this and are the ones that have formed this hypothesis. And it does seem to work. So the marshfield terrain would eventually collide with the Pembine here. The Pembine does extend down south a few miles. So the marshfield south of that even. And then we had all those granites I've taken you to see before, like the Spikehorn, the Amberg, the Asthenoline, and all the others in the Dunbar Dome. And all the others on the Dunbar Dome. So what you had going on here during that collision of the Pembine to the superior craton and then the marshfield to the Pembine is you had a forming of North America. You started to get North America building up. And this all happened during the Pinocchian orogeny. So there would have been huge mountains here, volcanic, at 1,800 million years ago. And to the very far north, you would start to get sediments deposited in the basin before that eventually filled in. So once a Paleoproterozoic craton formed of North America, you started to get more assemblage. And this is typical. North America basically built from north to a south direction. I'm using modern directions here. But I'm really interested to see what kind of rock this is. My guess is it is a peridotite. This color is very typical of serpentinization. It's an altering of ultramafic rock. Ultramafic rock is extremely susceptible to chemical weathering on the surface of the earth. If I was to throw acid on this, hydrochloric acid, weak acid, I bet it would fizz like a carbonate rock, at least on the weathered part. Anyways, that's it. If you have any questions or comments, please leave them below, and I hope you learned something. Here, this is the base. Oh shit.
You swallow a bug?
Yeah, I got a bug in me. So you have this, what was I going to say? Huge mountains here